Welcome back to Zone African Motives. We are still on our industrial electronics N3 that is working with the AC theory. We have got the part that you're going to consider, which is the series alternating current circuits. So if you still remember, you had or you worked with this part from your N2. If you still consider or remember that part of the CIVU that we had in our N2, if you still remember, when we applied the concept of the CIVU, when you're given a condition where you have got a purely resistive circuit that you're going to consider, when you are given a purely inductive circuit that you are going to consider, or maybe you're given a purely capacitive circuit that you're going to also consider in the applications. You were considering the voltage across the inductor, the voltage that you're given across the capacitor, the voltage across the resistor. But this is considering or referring to either an inductive or a capacitive circuit, which is taken at an angle of 90 degrees. But we want to know, is it going to lead by 90 degrees or it's going to lag by 90 degrees? This is on a purely inductive or capacitive. So you're considering in a capacitive circuit, you're considering the current leads the voltage, okay? If you are considering an inductive circuit, which is this part of the inductive circuit, you're considering the voltage leads the current, or you're considering as the current lags the voltage by an angle of 90 degrees. It's a purely resistive, purely capacitive circuit at an angle of 90 degrees. Then you considered, or if you still remember, you're also having this with an RC circuit or an RL circuit, where now you're given a resistor and an inductor. This was still your N2. You still remember that concept. You're going to have still the same continuation, having a resistor and an inductor that you're given. You're going to have the current that is flowing, which is the same. Considering in terms of the RC circuit, it's the same thing again. A resistor, you can have a resistor, a capacitor that you are given connected to an AC, in this case, a resistor and a capacitor. So in a normal consideration, we cannot have a circuit that has got an inductor and a capacitor. Okay, a circuit is supposed to have a resistive component. There must be a resistor in as a component of that circuit. So it can be RL or it can be an RC. You heard this from the applications of your N2. So in our major consideration of the N3 part, that is where we are working with the RLC, a resistor, an inductor, and a capacitor. This is the major part that you're actually going to be working with, which is an RLC circuit, resistor, inductor, and a capacitor in series. That's the major part that we are going to talk about. So just for the benefit of our N2 recap, the Phasor diagrams, this and that, in terms of the angles that you are given, we can consider just one or two of this part. Series alternating current circuits, understanding series RL circuit that you're given. Okay, very sorry for that. So if you're to consider this part, like I was saying, it is just simply an understanding that you're going to have from the N2 as it is, all right? You are working with a resistor and an inductor. What is it that you're going to consider in this case? The voltage that is across the resistor and also the voltage across the inductor. Remember, the currents is the same, which is the total current in a series circuit. We're going to have this current flowing being the same. It is the same current that we're going to have throughout the circuit. It's a series. This part is not going to change. current in a series circuit is the same. So meaning to say this total current is the same as the current that you're going to have across the resistor. It is the same as the current that you are going to have across the inductor. So I want you to go through this. This is like I was saying, from our N2 part, if you're to consider this, okay, the total current is equal to the current across the inductor, that one across the resistor also. Then in terms of the voltages that you are going to have in, it is also important that you consider the application of your N2 again in terms of the currents and the voltages. Okay, remember from the civil concept that I was explaining, but this time it is going to be affected by a certain angle theta, by a certain angle that is considered. If it is just a purely, if it's something that is pure, it means our voltage for inductive is going to lead by 90 degrees. But given at a certain consideration that it's no longer a pure, you're having an RL circuit. So we are going to have the angle theta in between, which is the phase angle that you can obtain this angle of theta from what you are given. You can consider from the voltage. That is the cos R of theta is equal to the voltage across the resistor over the voltage, which is the total voltage in this case, which can be considered from the resistance and the impedance. From the resistance and the impedance that you're given. If you're to consider the total voltages, in this case, our VT, which is equal to the square root, remember this is the square root of VR squared plus the square root of VL squared. You are considering the phasor sum of your voltages that you are given. So like I said, if you're considering the series part, guys, just make sure that you go through your N2 part. That is the introduction part that you're just having there, and also the summary that you are going to consider or to work with. So I want us to quickly rush through the part that is important. Okay, also the RC circuit, remember, if a given, is still one and the same thing as what we had on the inductive circuit when you're given an RC, an RL circuit, but only this time you're talking of the capacitor. So we are going to have, in this case, remember from that civil concept that you were working with, where the capacitor is in terms of the current and the voltage. The current leads the voltage, meaning to say the voltage lags the current. If you take from the voltage is lagging the current. That's why we see on the presentation the voltage down. On this side, it is lagging the current. All right. So it is one and the same thing as what you're going to, as what you had actually from the RL circuit. So I want us to work with what is important in our syllabus, which is the RLC circuit. In our syllabus, they need you to understand the basics of an RLC circuit. It is the one that you are going to consider or to work with. So those basics that you are given there, I just want you to go through, revise your basics, but this is what you're going to be working with in your syllabus. For series circuits, you're going to be working with the RLC series. Then you are going to have for the parallel circuit as well. Okay, so this is for series. Then we are going to also have for a parallel. So you must be able to understand these two. That is the series RLC circuit and also that one for the parallel. Okay. When you're given an RLC circuit, as you have to consider, you are working with a resistor, an inductor, and a capacitor. These are the two things that you are working with: resistor, an inductor, and a capacitor. So you're given something of this nature. So this is what you have. This is a resistor, this is an inductor, this is a capacitor, and you're given the current that is flowing. And remember, this is a series circuit where current is actually the same. Current is the same. So what they want you to understand is that in terms of the presentation that you are going to have, remember the calculation of the reactances is not going to change. You have got the voltage that is across the resistor, you've got the voltage across the inductor, the voltage across the capacitor, the total voltage that you are given at a certain frequency. With this, you can use the current as the same because there's a series consideration. Remember, in the series, current is the same. Current that you are having at the resistor, inductor, the same. So meaning to say with this, the voltage across the resistor is simply the current times the resistance. The voltage across the inductor is simply current times the reactance of that inductor. The voltage across the capacitor is the total current times the reactance across the capacitor. But these voltages, in order for these to give us the total voltage, you are not going to add this voltage, this like what you have on a series if you are working with those DC circuits. Remember from your DC circuits, if you are given resistances, I want you to correct this idea. If you are given R1, R2, you are going to be having V1 and V2, and this is the total voltage that you are given, and that's the total current. Remember, your total voltage, it was just the sum of V1 plus V2 direct. But this time, it is no longer that consideration. This total voltage is referred as the phasor sum of these voltages. The phasor sum, that means there is an application of the angle in between. So this is going to be determined by considerations that it's either we are going to have these conditions, the three conditions that you're going to have. It's either we are going to have this VL greater than VC. So it can be also in terms of the reactances. All right. If I talk about the reactance, that maybe you're going to understand much better. All right. Remember, across the inductor, there is XL. Across the capacitor, there is XC. So let's say if our XL is greater than XC, by just having XL bigger than XC, it also means VL. Therefore, in this case, VL is greater than VC. The voltage across the inductor is going to be greater than the voltage across the capacitor. That is the consideration. But in this case, if our XL is greater than XC, it means, remember, I want you to consider these things here. This capacitor cannot be considered, and you've got RL circuit, or you've got an RC circuit before. So it is the same sense that you're going to bring in this situation. You're going to bring the same sense to say, if XL is greater than XC, if this reactance across the inductor is bigger than that one across the capacitor, it means your circuit is more of inductive. It's more inductive in that case. So if it is more inductive, you are going to use the same properties that you had when you're working with an RL circuit. What is it that you're considering from the RL circuit, all right? That is the same consideration that you're going to apply. Okay, let me bring you back here when we had that RL circuit here. What is it that you're considering on the RL circuit? In terms of our RL circuit, this is the major part that you were having. I want us to consider in terms of the voltages. I want you to see where the voltages are. If you check, you are presenting your voltage VL on top. Why? Because we are saying in this case, the voltage is leading the current. Okay. So if this is more inductive, it means you consider it in that manner. It is more inductive. So let us go back to our civil. I want to go back to this so that you understand. It is more inductive, so you consider this part of the inductance. So in terms of the voltage leads the current. So in terms of the current, what does it mean? It means the current lags the voltage. The current is below. So current lags the voltage. So if you were to present now, this helps a lot because it is more inductive. So you're going to take it in an inductive manner, in this inductive manner, where the voltage leads the current, but it leads the current by a certain angle, theta, which is the phase angle. It's no longer at 90 degrees. So if you are to consider the phasor diagram in this case, it is going to be like this. This is the major part of your N3. If you are to consider the phasor diagram, you're going to see this time, remember, the voltage leads. The voltage is the one on top. So this is where we are supposed to have your VL. And this is where we are supposed to have our VC. The inductor, the voltage leads. Meaning to say, this is where our current is. Voltage leads. But in this case, remember what you're considering. It is the total voltage that you want to consider. So it is going to be given at a certain angle theta, not at 90 degrees. It is going to be taken at a certain angle theta. And at this point that we are taking, it must correspond to the difference between the voltage. Since our XL is greater than since our VC is greater than our VL is greater than VC, we are going to have the difference of VL minus VC. What is bigger than minus the smaller one? Remember, you're considering to be more inductive, so it must be on top. The voltage leading a current by a certain angle theta. So that is the consideration. So at this, it is corresponding, this value, it is the difference between VL and VC. Then the value that you're going to have in this case here is for the total voltage, which is our V, or our VT, which is the total current times the impedance. That's the total voltage that is there. And in this way, we are given the current. Remember, always the current is in phase with the VR. That is where we are given VR. That is the idea. What is more? What is it that you're considering? So in the same sense, by being more inductive as it is, it means in terms of the impedance, diagram that you're going to have at the end, we are going to have the difference this time. Remember, it's more inductive. So it's on top. The inductance is on top. So the Z that we are going to have, remember, this is impedance, we're talking about Z, but the Z is considered from the reactance. And since XL is greater than XC, this here is going to be the difference, XL minus XC, because this is the X is for what? This is for XL on top, down here is for XC. But at this point, it is the difference between XL and XC. That is the idea. Corresponding to what? To the resistance that we are going to have in this axis. So this is our Z, which is taken at a certain angle theta. So since these are taken at certain angles that you are given, and there's a difference XL minus XC, depending with what you're given, to say it is the XL or it is the XL which is bigger than this. It means at the end, the V and the Z will be the phasor sum. The V that you are going to have, considering this VT, which we are considering as the total voltage, it is going to be the phasor sum, which is our VR squared plus the difference between these two, which is VL minus VC squared. So it's going to be VL minus VC squared. On this idea, again, the impedance from the phasor sum, it is going to be R squared plus this reactance that you're given, which is XL minus XC squared. So that is the idea there. So the opposite now is true. The opposite is true from this part that we are given. What am I trying to say? The opposite is true from what we are given. If this consideration that we are given, if you are now given this time XC being greater than XL, if you're given XC is now bigger than XL, it means this circuit is more capacitive. And if it is more capacitive, you have to consider it from the capacitive manner that you had from your civil concept. From the capacitive manner, from this capacitive, current leads the voltage, meaning to say the voltage lags. If current leads, it means the voltage is below. V lags the current by a certain angle theta this time. So we are going to have these diagrams now down. This voltage, it was on top. So meaning to say this time we are going to have our phasor diagram with the voltage down here. This is where we are going to be considering, because VC is the one that we are considering to be more than our VL. So meaning to say we are going to have something like this in this case. And this value corresponding to the difference that you have, because at this condition, therefore, it follows that VC is going to be greater than VL, just like what we had before. So this will be the difference of VC minus VL, giving us the total voltage taken at a certain angle theta, just the same way that we had before, in phase with our current, and we shall have corresponding in this case to VR. So that means at the end, we are going to see that the formula, instead of us having this as a VT is the square root of VR squared plus VL minus VC squared, is going to be the opposite, because this time it is VC, which is bigger than VL. So our VT at the end, it is going to be the square root of VR squared plus the difference of these two, which is VC minus VL squared. So in actual sense, we can conclude that what is important in all this part, it is to understand the type that you're working with, the condition that you are working with. What is it that you are working with at the end? If you are to consider these reactances greater than, in this case, this is a change. It can be XC minus XL. It's not like XL minus XC always. It can be XC minus XL. Which one is greater than? Instead of having VL minus VC, it can be VC minus VL. Which one is bigger than? So on these formulas, that's why it's not a direct minus that you are given there, because it can be opposite. So you need to understand that. It can be opposite to what you are given there. It can be opposite. So this is what I'm trying to say. Questions might be given like this. So do not even, it's just a continuation from the normal RL circuits that were used before. In Fig A that we're given, calculate A, the impedance, the total current, this and that. So as you can see in this case, you are given an RLC circuit, having a resistance of 25, the inductance 0.19, the capacitance. And you need to calculate item 1, the total impedance of the circuit. So the impedance, which is the total impedance of the circuit, as we saw from that case, it is affected by the reactance that you're given, XL and XC, these two, because we need to compare, is XL greater than this or is XC greater than this? So meaning to say there is a need for us to calculate the reactances, the reactance across the inductor, which is our XL from 2 pi FL the reactance across the capacitor also. All right, so the reactance across the inductor from 2 pi FL, that is 2 pi times the frequency, which is 50 Hz, times the inductance, which is 0.19. So this is going to give us the reactance that is something like 56.69 ohms. And also, if you're using the textbook, sometimes they round off to 1 decimal place, sometimes they round to 2 decimal place, sometimes they round to 3 decimal place, and at the end, they affect even the answers at the end. So if you're using a certain decimal place, maintain that. So in this case, I was working with the 3 decimal place, but at the end, this was going to be a 0, so it was going to be 56.69. Then the reactance across the capacitor, remember, from a 1/2 pi FC, this is not going to change, guys. Remember your N2 formulas, and also you are given, you've forgotten these formulas, the formula sheet, you are given the XL and the XC, so you can also relate from there. So that is 1/2 pi times the frequency that you are given, which is 50 times the capacitance, that is 125 times 10 to the exponent of -6. So this we are obtaining the reactance across the capacitor, and that was going to be 25.465 ohms, that is to 3 decimal places. So with this, remember what you want to calculate is the impedance, but this impedance is controlled by these two. So we must check across, according to these two that you are given, the reactance of the inductor and that reactance of the capacitor. Which one is bigger? As we can see, the one for the inductor is greater than this, 56 is bigger than that. So XL is greater than XC. The reactance, this is what you're going to be focusing with. You're not going to have just a direct RC circuit or RL circuit. It's going to be RLC. Everything considered in a single circuit. So you must compare which one is bigger between these two. Because we saw that from the impedance that you are given, it is controlled between VL and VC. So is it XC or is it, between XC and XL? So is it XL or XC which is bigger than? In this case, it is XL. So therefore, our Z, it is going to be the Phasor sum, which is the square root of R squared plus the difference between these two, which is the bigger one minus the smaller one. So it's XL minus XC squared. So you can substitute the values. Remember, we've got the resistance, that is 25 ohms. So that Z is going to be the square root of, so you're going to have 25 squared plus XL, that is 56.69. So in this case, you're going to have 56.69 minus the difference that we are, minus this 25.465. Sorry for that. So you're going to subtract this. So like I said, due to the rounding off of your answers, if you maintain, keep that decimal that you are working with. So to 3 decimal places, you're going to have 42.383 ohms. So this is the total impedance that you're given, the impedance of the circuit. So the impedance, this is just like resistance when you're working with DC circuits. Remember, you're calculating total resistance, but it's different from, like, we are working as the Phasor sum. There's an angle in between. So remember your the applications of our Pythagoras theorem. That same application is the one that we are working with. So you must be able to consider formulas, what is important from the formulas that you are given at the end. Then from the other part on B, we are given the total current. So as we can see, there's a series circuit and the current is the same. So you can consider from the total voltage and the total impedance that you are given. And also do not worry about this if you've forgotten, because the formula sheet, you're also assisted. The total current is the total voltage over the total impedance. So from there, you can relate how to calculate this total current that you are given. So that is the B, the total current from the total voltage over the total impedance that you are given. Remember the voltage, 200 volts. from the supply that you're given and the impedance from what we have. This is 42,383. So if you are to divide this, you're going to obtain the total current. So like I said, if the decimals that you work with actually can even affect our answers. So from what I've maintaining these 3 decimal places, I was going to obtain 4,719. So if you're working with textbooks, sometimes it's difficult that you see a round off to 2 decimal places, 1 decimal place, like I said before. But under an exam condition, you're supposed to maintain the 3 decimal places. You cannot know this one I'm going to round to 2 decimal places. This one I'm going to round to 1 decimal place. This one I'm going to, so maintain your rounding off part. If you're maintaining to 2 decimal places, maintain, but let's maintain the exam part, which is the 3 decimal places. All right. Then C, it was the voltage across the coil. So this is the coil. So when you're considering the coil, you're considering the application, the combination of the resistor and the inductor. That's our coil. So in this case, you're considering the inductor and the resistor combined. That's your coil. So meaning to say we need, because what we need is the voltage. So we need the impedance of this coil that we are given. We are going to need the impedance of that coil, because the voltage across the coil, it is supposed to be taken from the total current times the impedance that is across that coil again. We have the resistance, we have got the reactance of the inductor, but what about this? This is an RL that you're considering, the resistor and the inductor. Remember back there when you're given a resistor and an inductor, how are you calculating Z? Z was equal to the square root of R squared plus XL squared. Remember that. You're just working with a resistor, and the resistor and the inductor that builds up a coil. So meaning to say that is our Z coil. So our Z coil in this case was going to be the square root of R squared, the resistance, that is 25 squared. So you're going to have 25 squared plus XL. Remember, from what we calculated, it was 56.69. So this is 56.69 squared. So that was going to give us our Z coil, which is the resistance, or in this case, we talk about the impedance, just like the resistance. You're saying this is the resistance of this part. That is of the same nature, that impedance that you need. Without the impedance, we cannot have the voltage. So that was going to give us 64.7. It was going to be 714 ohms. So this is what you're given as the impedance across the coil. But what is the voltage now? From this formula that we are given, we are saying the voltage can be taken from the total current. Remember, you calculated the total current before. So you're going to consider your total current. That was 4.719. Okay, so you've got the total current 4.719 times the impedance across the coil, which is 64.714. So this is what you're going to have. So with these guys, we are going to have the voltage, which is across the coil, and that was going to be 305.385 volts. So that is what you're going to have at the end, the voltage across the coil. So maintain the degree of accuracy that you are working with throughout. Then that one of across the capacitor, we are going to use the reactance of the capacitor in this case. Across the capacitor, remember, our reactance XC. So meaning to say the voltage across the capacitor also from this, it is from the same consideration. Okay, we can even just write it here, where we have got this XC already. So this is our D. So the voltage across the capacitor is current times the reactance that you are given across the capacitor. The current, remember, in a series, the current is the same. So we are going to consider the total current that we calculated before. Remember our total current, the one that we calculated, that was 4.719. times the total reactance, the reactance across the capacitor, which is 25,465. So this is going to give us the voltage of 106,418 volts. All right. So for those who are actually working with this textbook, actually you can now see that the answers that you're given there, they're a little bit different. It is because of the rounding off of the values at the end, like I was explaining. The moment you're dealing or you're working with the decimals and you round off them differently, they affect a decimal. It affects a lot in your calculations. So maintain whatever that you are using, 3 decimal places, maintain it like that. Do not even worry about what is there. Maintain the 3 decimal places that you are working with. All right. On question number 12, we are given a similar consideration, but this time they have already calculated the reactances. We are not given the inductance, we are given the reactance of the inductor and also the reactance of the capacitor. We are not given the reactances. And the question is to calculate A, the Z, which is the total impedance, just like the previous case that you're given. So in this case, already the reactances are there. So what we just need is to compare between that of the inductor and that of the capacitor. Which one is bigger? As we can see, our XC is greater than this XL. All right, our XC is greater than XL. It is bigger than XL. So if it is bigger than XL, therefore the impedance will be the phasor sum, which is R squared plus it's going to be XC minus XL. So this will be XC minus XL squared. Just like what we had before. But what we had before on this question, it was which value which was bigger? It was the XL, which was bigger than X. So it's supposed to be XL minus XC. And also these reactants, it is you who calculated these reactances, but this time you're given. What you just needed was to compare. You're already given the reactances. This is an ohms. Take note of the units. Ohms, reactance. Inductance is measured in henries. Capacitance in farads. Remember that. The ohms are for reactance. So that is supposed to be put into consideration. So Z is equal to the square root of R squared. We've got our resistance, which is 40 squared plus XC. XC, remember, this is 60. So that is 60 minus XL, which is 40. So if you subtract this squared, that was going to give us the impedance of circuit in this case, which is the total impedance, actually 44,721 ohms. So this is what you're going to have at the end. Then B, the total current. So from this, we understand this is a series circuit that you're given. And in a series circuit, the current is the same. So you can also consider, just like the previous case, the total current from the total voltage over the total impedance that we have. We are given the voltage across of 220. The total impedance we calculated. So this is 220 over the impedance that we calculated, 44,721. So that was going to give us the total current in this case, which is going to be 4,919 amps. Just like that. We have these values. We have now. Then they want you to calculate L. This is for the inductance of the circuit. What is the inductance there? Remember, your inductance measured in henries. Since we are not given, we are given XL. So from XL that we are given, what is going to be the inductance? You need the inductance. So from our XL, we are given the reactance XL. Remember, XL is 2 pi FL. We can calculate this inductance. Divide by 2 pi f. Divide by 2 pi f both sides. So that is the inductance is equal to XL over 2 pi f. That's our XL in this case, all right? We have got this XL from the circuit that you're given across the inductor. Our XL, that was 40. So that is going to be, the inductance is going to be XL, which is 40 over 2 pi times the frequency. Remember, our frequency, it was 50 hertz. So that was going to give us 0,127 henries to 3 decimal places. Remember, inductance is measured in henries, just like that. Then the capacitance also, just like the inductance, where are you gonna obtain this capacitance that we asked to calculate? Remember, from the reactance again, you have the reactance of the capacitor. You have got the reactance of the capacitor. So from the reactance of the capacitor, which is given as 1 over 2 pi fc, you're going to make see the subject. Remember, I talked about this. You can make see the subject. You're going to cross multiply. That is xc times this. So it's going to be 2 pi fc times xc, which is equal to 1 times 1, which is 1. Remember, what you need is the capacitance this time. So you're going to divide by 2 pi f times xc. So you divide by 2 pi f xc. So this is going to cancel your remaining with the capacitance. So the capacitance is going to be given as 1 over 2 pi f xc. So if you have to check, it is just for an capacitive circuit, you just interchange these two. XC is equal to this. Capacitance is also equal to this. It's just interchanging of that. If you understand that way, you can just make it short. Instead of making all this the subject of the formula, you just need to know that, okay, this one interchanges. So you can actually make it or take it that way. So this is the formula that you need. So with this, you can substitute. So this is 1 over 2 pi times the frequency, which is 50 hertz times XC. Remember the reactance across the capacitor, we are given as 60. So capacitance, in most cases, we are going to say we take our capacitance to be in microfarads. Yes, it can be picofarads, depending with what you are going to express your answer as. So if you have to express in microfarads, where we know that the microfarads means times 10 to the exponent of -6. It means, so to convert to that microfarad, you multiply by the opposite of that -6, by the inverse of that, which is times 10 to the exponent of 6. Your answer will be automatically in a microfarad. Yes, microfarad means times 10 to the exponent of -6, but to convert to that microfarad is the opposite, the reciprocal of that. So that was going to give us the answer that you obtain on your calculator, as it is 53,02,052. The answer that you're obtaining as it is automatically now in microfarads. So you are obtaining that answer in microfarad by multiplying by 10 to the exponent of 6, which is the opposite of what you are to consider there. So this is it. That's how these questions might be given. And E, the phase angle. I want you to understand about this series. It is series RL, RC, series RLC circuit. All about this. If you are to consider this here, it answers everything about our series circuits here, this part of your formula sheet here. All right, the XL, XCs can be for both reactances, but these are the major formulas for series. So if you check here, there's theta, which is equal to arc cos R over Z. Arc cos R over Z. That is the one that, with this one, you're not going to go wrong, guys. For any series combination that you consider, theta is equal to arc cos the resistance over the impedance. So theta is equal to arc cos the resistance, which is 40, over the impedance, which we calculated before. Remember, this one, we have already calculated this impedance, 44,721. So that was 44,721. So this is arc cos. On your calculator, shift cos this, you were going to obtain something like 26,564 degrees. That is how you can consider as the phase angle that is between the two, between remember, you're considering between the current, the voltage, or it can be from the impedance triangle, the impedance diagram, which is the one they're asking you to draw the phasor and impedance diagrams with a phasor or with an angle of 26,56 that we got here. What is important on your phasor or the impedance, guys, is what I explained on that first part. What is it that is bigger than? XL is XC is bigger than XL. It is our XL which is greater than, with this consideration that we are given, that this is bigger than. That alone, it can help us to answer this. So I'm just gonna guys, this is just a recap. I'm just gonna have a recap, then you fill in the diagrams. So in terms of the phasor, I don't know, you're gonna consider, I'm just gonna consider in this case in terms of the voltages. Remember, I said if XC is greater than XL, it also means the same thing. Our VC is greater than our VL. And in that case, from the civil concept that you are considering, it is more capacitive. So under a capacitive circuit, the current leads the voltage, meaning to say the voltage lags. So we are going to have our voltage this side, VC. It lags. So, but the major part is that it is going to be the difference that you're going to have, which is a VC minus VL. Remember, this is the axis showing VL, VC, but it must be the difference VC minus VL at an angle theta taken corresponding to our VR, and that is in phase with what? With the current. Remember that you have got all these values, so you can even write these values, there's no problem. From the impedance diagram, again, it is the same thing. It is going to be taken down because the voltage is lagging the current. So it also follows the same thing even for the impedance. This is where we're going to have our impedance corresponding in this case, which is the difference at this case of XC, the one that is bigger, XC minus XL. Okay, this is the axis of our XC. This is the axis of our XL, remember, which is taken corresponding to a certain resistance, which we know that it is in phase the voltage. You can also consider in terms of the voltage that you're given. So this is going to give us Z. In this case, we are having the total voltage, which is VT. You have got all these values, so you can also write the values that you are, all the values that you are given on that diagram at the end. So this is what they want you to understand, because they are going to give you an impedance or a phasor diagram of this and ask you questions just like what you're answering here. You have to do the same thing. It is the same application that you are given from the phasor diagram that you are given. You can also analyze it back to the voltages, analyze back to the resistance and the reactances from the impedance diagram. What is it that is bigger than compared another part? That takes part of the major diagram. If it is XC, it means your circuit is more capacitive. If it is XL, which is bigger than XC, it means your circuit is more inductive. So you consider those consider in each and every part that you're going to answer these typical questions. So you shall have more questions. Actually, there's another part I want you to check, the resonance. I talked about that resonance of the series AC circuits. So make sure that you go through, and also join membership. By joining membership, you can also have access to other videos that are here, that are already on the N3 part, also considering the parallel and other revisions. So it can help us as we are moving together as a family. Join membership for N1 to N4 studies.